Hello and welcome to YMT217 programming languages. We are still discussing preliminaries. This is the third part, and in part 3 we will focus on influences on language design, language categories, and language design trade-offs. Initially, we have to explain or actually elaborate on the idea of actually the design of the program language or programming language. If we are to design a programming language, we are designing this language based on what? So what's the perspective we are designing the language for? First of all, the factor or the main factor that we have to take in our consideration is we are going to use this programming language on what machine? So if you're going to use it for the standard computer, the standard machine that we are using for our computational processes, then we are going to use it for the standard, what we call von Neumann architecture computer. Von Neumann, you guys have studied von Neumann, and actually in Introduction to Computer Science, I believe you studied this. But just to revise the idea, it's actually an old design of, or an old architectural view, not design, I'm sorry, an old architectural view of our computing system that lays out what? Lays out the following. A computer has a memory connected to a processing unit, central processing unit, which is actually receiving data from input and sending whatever results or processed data to output. So we have input and output, and we have a central processing unit, and this central processing unit is composed of arithmetic and logic unit plus some control structures. And this central processing unit requires or needs a memory to store data and instructions needed for processing in it. So this is the basic idea of von Neumann architecture. I can show you the diagram here. Look at this. We have the arithmetic and logic unit for processing, arithmetic calculations, logic operations, and so on. And we have a control unit. So altogether they form the central processing unit, and we have what we call instruction and data stored in the memory. Memory here in this case, your computer's main memory. This is pretty much similar to the architecture of our computers nowadays. Now, it's pretty much close, okay? So there is a processing going on, and we need to fetch the data, bring it from the memory, and then after we produce the result, it may be displayed to the output or it may be sent to the memory. Even if it is to be displayed, we may need to store some part of the outputs in the memory until we compose all of it. So this is the idea. Now, if we are to design a language, we have to put this one into our consideration. We have to include it in our consideration so that we know what kind of a language we are designing. So computer architecture is the first and foremost actually factor that influences whatever design of a programming language we need to achieve or we need to take. Alright, so based on that, if we are designing programming language, we need to think about the von Neumann, and thinking about von Neumann, we speak about memory. So the idea is, instructions. The instructions of our programming language must be stored in the memory and fetched from the memory. Well, okay, so what are we speaking about here? Well, we speak about data, instructions, and data. Well, that takes us to something what we call imperative scenario. So most of the time we speak about the design of programming language, we have to be guided back again to somehow imperative way of programming. Imperative way of programming means do something. So we instruct the computer to do. So we provide an instruction to the computer, and the computer will do what? Will execute it. Fetch the instruction from the memory. Fetch, that means bring it from the memory, pipe it to the microprocessor or the central processing unit, achieve what is needed from it. Of course, after decoding it, we'll explain about it in a while. Then produce the outcome, store it in the memory, or do the next step. Now, you may wonder that, wait a minute, it's all about data, it's all about simple processing things. How about object-oriented? This is a new paradigm, actually, of programming languages. We'll speak about it in a while, but it has also its base, which takes us back to von Neumann machine or von Neumann architecture. So I hope the idea of the von Neumann architecture is clear, and why we have a concept, we call it imperative. Now, imperative language, as I said, we instruct the computer to do what, actually? Well, process something for us. Process it based on what? All right, so we are processing some data. This data must be stored somewhere. So stored somewhere, we need a memory, storage capability. Okay, we have it. How about a processing data based on what? So how do you want me to process this data? I have to have instructions to process the data. So let's say if I want to add X and Y, I have to have some procedure to add that. Maybe some symbolic representation of an operator. Let's say the addition plus sign. It could be one of the possibilities. In that case, the computer will understand it, interpret it, or translate it to add these two, let's say, variables or quantities. Okay, so we have data and also the instructions, programs to be stored in the memory. This is number one. The memory itself, I didn't say earlier, the memory itself is separate from the central processing unit. And you guys also studied this in Introduction to Computer Science, and you know the reason why the memory has to be separate from the processing unit. If you forgot, please double check this one. It's not actually included in our course, but it's for your general knowledge why this memory is supposed to be separate. Okay. Next to that, so we have a central processing unit, and we have a separate memory where instructions and data that we need for our calculations or whatever logic expressions to achieve any result from a program. Then how can we process? We need to pipe or fetch the data and instructions from the memory to the CPU in order for us to process them. So this is exactly the basic sense of how a program is done based on von Neumann. So now let's just discuss this. Imagine we have variables which represent data, okay, so they model data. We have assignment statements. Assignment statement, in the most basic sense is we can say, let's say x equals to 5 plus 10. Or maybe x equals to y plus z. Y and z are stored in the memory as 5 and 10. Okay? So we have assignment statements. These assignment statements require us to pipe some data from the memory. And when we say variables, and you guys studied variables also in your first course of algorithm and programming, also in the second one, it's actually in the basic or elementary definition of them, in this case, a named memory cells. Now, this one, look at this here, I'm sorry, look at this. The memory here, virtually, we can display it this way, or we can illustrate it this way. This is not the real view of it, this is not the physical view of it, no, it's just a virtual view or something that we can illustrate the memory with. We can just put strips next to each other, like memory cells. We call this as a cell. Now, it depends on the type of the memory of your machine. This is not the point now. So this is a cell. We can give it a name, X or Y or Z, based on its own address, and it will be a named memory cell. So whatever the content here will be represented by X or Y or Z as a variable. That's why we call them variables. They change based on the value assigned to them, and they name a memory cell. So we need to pipe them. Pipe them, that means bring them, fetch them from the memory and bring them to the processing unit. Okay? And next to that, we need to repeat certain procedures to do this over and over again. Okay? Well, this is exactly the idea of von Neumann machine, and that is why what we call is usually we have a base for imperative languages. Do something. Okay, bring an instruction, bring a memory. So use this variable to bring the content of the memory. Repeat the process over and over again. Now one more thing about iteration or repetition we explain here is for von Neumann we need a continuous repetition of certain instructions. And in that case, what happens? Now these memory cells, when we store the instructions of a program, it happens to be based on the standard procedure of storing the instructions of a program. It happens to be that like they are next to each other in adjacent cells. And accessing to them doesn't require much of time. Why? Because when we access them, there is something we call program counter that takes us from one cell to another based on a certain increment. Okay? So it doesn't take much time to locate the next instruction or to move to the next instruction. That's important in computing. Why? Because it's a matter of efficiency. Time is a matter of efficiency, and you guys are studying this in data structures now. Saving the resources of computer, both time and memory, is an efficient procedure we usually do whenever we discuss any algorithm. Okay, so in this case, the iterative procedure fits the von Neumann machine more than recursion. For the recursion, what do we have? We have a different scenario where the stacked actually, or the recursed steps are not stored in adjacent cells. Not likely they would be stored in adjacent cells. There is no standard procedure for them to go through this process of adjacent memory cells for storage. And in that case, we need to access to each and every one of them each time we jump somewhere to get the memory and get to the final step of the recursion, and that takes time. Now, iterative process is more efficient for von Neumann machine, and that's why it is widely used in imperative language. Although actually the recursion itself looks more natural, or it is actually the natural process of doing things repetitively in our life. However, in this case, repetition looks much efficient for such a machine until maybe some of you guys will invent some new architecture for a computer that doesn't actually coincide with the von Neumann machine, and in that case maybe some recursion or any other procedure would be more efficient. Until then, the iterative or the iteration for repetition will be carried out in most cases. So let's go next to that. So we explained about the von Neumann architecture and what kind of language that fits this architecture. Now let's speak about the execution itself. So I said we have the data that we need to process along with the instructions of the programming language stored in our memory. Okay, so in order for us to execute them, we have to carry them. Or this is what we call in scientific term, or in this case, a more technological term, we fetch them. So we bring them to where? To the central processing unit. So the central processing unit will do something we call execute. Executing the instruction, whatever the instruction is, it doesn't matter now. But what we need to say is like what we call fetch execute. So fetch execute is exactly a cycle, or it's done based on a cycle, and we will explain about this fetch execute cycle later on, not now. But it is done this way. I'll come back to these, don't worry. We initialize a program counter. And what's program counter? Now think about this. For any program, using any programming language, we need to initialize where to start, and we don't do it manually. This is done by the program itself. So we have to initialize which address we have to start with. So each programming language has its own instruction to initialize from where to start. Okay, And from where to start, so what to carry from the memory, which address I should bring its own data in order for me to start processing. Okay, so this is called program counter, and this is a register. And you guys are familiar with the register type of a memory. It's very fast and small, attached directly to the processing unit. Okay, so fetch what? Fetch the data addressed by the address available in program counter. Okay, so we have an address. Because this memory cell is like, imagine it's a house that has an address. Okay, and the house may have a content, a family in. So in that case, it has an address. We can access this memory cell based on its own address. So this address will be available in the program counter. Okay, so initially we have certain program counter, we access to it, we see what's supposed to be carried from the memory, we bring it. So bringing it is called fetching. Once it is fetched, brought to the processor, then we execute it. We see the available instruction or operation that we need to do. It will be executed, then an outcome will happen. Now what is next? What is next is program counter. Once we fetch the data address somewhere in the memory available, its address is available in the program counter, it increments the counter. Like counter, let's say its name is counter, let's say program counter PC++. It increments it, it goes to the next cell. And that's why I said we have adjacent cells in this case to execute. Okay, this is the process, the standard process for such an imperative language design. All right, so this is the idea. Program counter will have a new address with an increment, which is an increment of the previous data was available in it, or address was available in it in this case, because address actually is a number, but I don't want to refer to it by data. I would just say it as an address of a memory. Okay, so we come back to the fetch execute cycle. We'll call this fetch execute. It's extremely important. We fetch the data from the memory based on the address available in program counter, and then we execute it. We not human beings, by the processor. The microprocessor or the central processing unit will execute it, and it will see what's needed. Maybe input or output is needed while executing. Okay, and then it will move to the next available address, because the program counter is automatically incremented once we fetch a content of a memory which is available addressed by a current program counter. So this is the way, this is the algorithm represents how fetch execute cycle is running. Initially the program counter is initialized. Now we don't do it, it's done automatically by the programming language, and repeat forever until we until we terminate this process. Fetch the instruction pointed by the counter or the program counter. So we need to fetch that instruction, increment the counter, decode the instruction. I forgot to say about the decoding, now I'll say about it. Now here's the thing. We said earlier, now it depends when we are, what kind of instruction we are bringing or fetching, okay? So in order for us to execute this instruction on data, we need to decode it. So decoding an instruction means finding what it means. What is this instruction supposed to mean to me? Okay. Every instruction in a programming language has its own decoding method, has its own code. Sorry, and it has to be decoded. And once it is decoded, it will tell the processor this instruction means, let's say, add these two quantities, for example. Or it will tell, okay, store this quantity somewhere, or point to somewhere. This means bring the memory pointed to by something. So that's that's what it means, decoding the instruction. Then execute the instruction. Execute, apply this instruction to something, data most likely. So variables or data residing in the memory, or maybe input, data coming from input, or maybe from a file or whatever. Okay. Once it's done, and repeat. So this one will keep on doing until our program is over, actually, until the program counter goes to somewhere that terminates the program. We'll speak about that one later on. And this is the fetch execute cycle. Usually we ask a lot about fetch execute. This is just an algorithm, and you guys know how to write an algorithm. This is not written by any programming language. It's just description of a code that if we would like to write it in a programming language, we can write it based on these steps of the algorithm. All right, so how programming languages, or the methods for actually design of programming languages changed throughout the history. In the last session or previous one, I'm not sure. Actually, part 1 or 2, we spoke about the early time of programming languages, where actually designers or scientists worried much back then. Worried much about what? About the machine more than the language. So all their design was concentrated on saving the resources of the machine. They didn't have powerful machines like the time we have now. Okay, so the efficiency of their machines was extremely limited, and for that reason they were having simple programming languages applications, or actually they focused on a programming language that saves resources. That was the common theme in 50s, 60s, even 40s if you would like to consider. Okay, so this is the idea. But if you remember, also I mentioned about the war, the Second World War in 40s, and I said right next to that, what happened is like people started turning to their own business. So we are not interested much in producing weapons more than just turning to business, turning to something more beneficial than war. We are done with the war, we want to settle, we want to make more useful things. So that is where the ideas of business started kicking in, and well, we need better programming languages for business to run our business. So the idea of structured programming started coming up during that time, beginning and late of 60s times. So more efficient programming languages. Why more efficient? Now the idea is like this. Well, we have the hardware. How about if this hardware, we reprogram it with efficient language that produces much of that hardware? Instead of actually developing the hardware, how about we develop the software? That's easier, right? For sure. That's why the development of software is usually much more faster than the development of hardware. This is the common theme in our reality. Okay, so readability was a major consideration. Also, the control structure was also among the main factors that they were considering. For that reason, what happened? They invented something we call top-down design. Top-down design, I explained it to you guys if you remember last semester in Principles of Software Engineering. We said about it like we break down a procedure, or maybe you can say an algorithm or a design or whatever, to steps. And we go from top to down by sub-procedures or you can say routines, until we manage all the problem. It's easier for us to deal with a big problem in pieces rather than just solving all of it at once. And also stepwise refinement. Stepwise refinement is extremely close to the incremental model in software engineering. So the incremental model says like this. Well, how about if instead of creating a software based on pre-planned scenario, what we do, we create a draft, and then from that draft we create a second draft. We ask the feedback of the customer or maybe the user, and then we create another refined version until we reach to the final version. Stepwise refinement works based on the same process or the same concept. What do? Initially we have a rough design about maybe a software or a programming language or whatever you may imagine. It's a software ultimately, okay? And then what we do is we start gradually going up with the design until we reach to the final code. Final code means an executable file for a software or maybe a programming language. It could be also an executable file, or maybe the final program if we are writing a program. Okay, that is these concepts came in the late 60s, and they left their own print on the programming language. But yet, that's not exactly the end of it. Why? This was focused on data. As I said, people were interested much in processing data for their own business, for their own development, scientific development, and so on. They abandoned war, not totally, but at least they turned to their own life. So we are not interested in weapons, we are interested in our own life, so we need to play with numbers and create useful things out of them. So data. The main theme was data. In the 70s, a new style came to the existence back then. A process-oriented. A process-oriented means what? Well, okay. Instead of dealing with data directly, how about we create procedure, and based on this procedure, we apply this procedure to data. Okay? Well, that's interested. How about if we directly take the data and create our own procedure with it and use that procedure? This is what we call data-oriented. So what kind of procedure can we create? You guys studied in Java things related to classes, things related to data hiding and similar things like that. How about data abstraction? We disregard or ignore whatever is relevant to our own interest or the reader's interest, and we keep what the reader or what the program actually cares about as an input for interfacing the data, and we hide the rest. This is what we call data abstraction in this case. Okay, abstraction is applied a lot in our life, and we have it as a concept, but it's a bit higher than the one in 70s. Why? I'll give you a simple example. Now, we said about process-oriented, moving from process-oriented like structured programming to data-oriented. Now we deal with data, but it's not exactly for data the interest nowadays. It's actually more about objects rather than data. Why? Data keeps changing. Data, we may have different types of data, but how about object? Well, if I encapsulate the data and the procedure applied to the data, then what I'm going to have is something like a versatile object that can be applied in many cases, and we can have its methods applicable to any other similar encapsulation of an object. It just needs to be the same object specification. You studied this in Java, but let me just remind you, with object-oriented, not data-oriented, with object-oriented we have what? On top of the data abstraction, we have inheritance. And you remember how powerful tool inheritance is. Inheritance as itself allows actually data reuse, and it makes more efficient runtime actually programming maneuver or style. Okay, polymorphism as well. It's also an interesting part of object-oriented programming that helps us to apply different ways or different assignment or different referencing way to the same object or the same class sometimes, if you like. All right, languages categories. Now languages can be categorized into different paradigms. However, we are not going to have like a consideration for all these categories. Why? Because it will be endless. If you just run a search about programming language categories, you will see a lot of way of categorizing for the language, or a lot of procedures for categorizing the languages, or you may find different categorizations for programming languages. Why? Because as I said at the beginning of this session, languages can be categorized, can be implemented from the perspective we look at it. So if you want to categorize it or even implement it, what kind of perspective are you considering? Okay, the way it is running or the way it runs, then you can have one perspective. The way it is oriented, another perspective. The way it runs on the machine, another perspective. So there are so many ways. However, we can just think about the orientation of the language itself, and then we can come up with this kind of general categorization of the language. The first category, we can call it imperative, and I explained about it earlier. Imperative means the use of variables, assignments or assignment statements, and iterations. And that fits 100% the von Neumann idea or architecture. Okay. How about object-oriented? Will it fit this kind of imperative language? Sure, yes. Why? I give you a simple example. If you check C language, which is totally structured language, and Java, in their own assignment statements, in their own variable declaration, and in their own iterations, they fit to a very high extent. They have like more than 90% match. The difference only when it comes to like orientation, object-oriented. Well, object-oriented in C is not applicable, but in Java it is. But yet, in that case, for the imperative nature, both of them hold. It's true for both of them. So, structured language can be imperative. Object-oriented language can be imperative. Also, scripting language can be imperative, like these two are scripting language, Perl and JavaScript. So, practical extraction and reporting language, Perl, is also one type of the markup language, not markup actually, scripting, okay? Visual Basic also is an object-oriented, but in that case, it applies to the same concept of imperative. C++, which is actually, you can say the updated version of C, is a bit higher than C, and it has also object-oriented nature. It can be used as structured language, but it can be also used as an object-oriented language in some sense. Okay, so scripting, also the visual languages. Visual Basic is called visual language, Visual Basic.NET or whatever language that you think as visual. Also Delphi, also considered in that case among these languages. Functional. Now we explained about the idea of imperative, order the computer to do something based on variables, data, and assignment statements using iteration. Functional, when we think about the functional way, now this is the idea. Instead of using actually assignment statements to do certain procedure with data, how about if we use functions to achieve whatever the computation requires? Instead of using assignment statements and data, we apply functions to whatever parameters we have as an argument given to these functions. Now think about, you guys studied this also before in Java. Let's say we have the class math, and this math has a method called sqrt, square root. So this sqrt method, or a function in this case, will get you the square root of any argument, that passed in this case as a parameter. So the parameter here will allow us to produce some result or outcome based on a functional procedure, a function, not imperative. In this case, we don't have iteration to produce. We don't have exactly an assignment rather than with functional procedure. What kind of languages apply to this? We have a very good example. Lisp is Lisp processing language. We explained about it. It's extremely functional. It uses a lot of functional procedure to produce the outcome. Scheme also. Maybe Scheme is not that much popular, but this one applies to it. ML and F#. This is pronounced F#. Maybe throughout your study, you guys, maybe you will not come across those except with this course, but we will study some examples about them and how they, operate and run, how we can write instructions with them in basic sense. Not now, later on. Okay. Logic. So we can categorize programming language based on their logic nature. And what does it mean? It means if we have a language that works based on rule-based, not data and variables and assignments, also not with functional procedure, rule-based, if we have like if-else, for example, procedure, or there is no, as we explained in logic circuits, in that case, we have one type or one category of programming language. The most prominent example of such languages is Prolog. And Prolog itself is being updated. This is a very interesting part. Prolog itself has a version called Prolog++. Okay, like C++, and it has also object-oriented nature. So you see the idea. We may have a logic, a rule-based programming language which is object-oriented. And we may have an imperative language like Java which is object-oriented, or structured like C, and so on. So they actually we have like some interleaving between the categorization somehow. We have another category, we call it the markup programming languages, or actually hybrid language. A language that is, you can say, a mix between two types or more. And in that case, the most common example, the languages that actually help us to create scripting, the hypertext markup language, HTML, usually in science, or maybe in this case in programming language sense, we don't refer to it as a complete programming language. Rather, we refer to it as a tool that helps us lay out a website or pages for a website. But for some reason, we can add some extension or extend this HTML by certain functionalities. Like, for example, I give you this one, JSTL, which actually refers to Java Standard Tag Library. So it's a library for tag, and these tags are extremely important for HTML, and they have the sense of programming language. If we add them to HTML, then we have the markup language. Okay. Also, this goes very well with the extensible style sheet language transformation. I'm sorry, not translation, transformation. Okay. This goes along with it. If we incorporate it with a markup language, then we will have a programming language in this case. Okay. So we spoke about the categorization of programming languages. Let's speak about trade-off. Trade-off is, in basic sense in English, means like you give up something to gain the other. Okay, you trade off, you compromise. We compromise what with what? We spoke about the factors that affect or influence the outcome of a language. Do you remember we spoke about readability, writability, reliability, and the cost? How about if we want to gain all these factors in one language? It's not practical. You can't have all of them in one language. Then what you need to do is you have to maintain certain acceptable level of all of them. Why? I'll give you a few examples about why. Reliability usually contradicts with the cost. Cost of what? Not money. It may be, ultimately maybe money, but what we speak about now is the cost of execution, the time, maybe the memory, the resources. Well, the resources now are not a big deal to speak about in terms of the memory. We speak about time, okay? So the idea is like this. If you want your programming language to be reliable, then in that case, you may give up from the speed. You need to give up the fast speed of your execution, or at least some of the expected speed of the execution. Now I give you a simple example. You guys are familiar with it. You studied Java before, and for those, I think all of you studied Java before. For those who are not familiar with it, now I'll explain about the idea. If you create an array, whatever type, now Java itself makes a bound check. It checks if you are using any index or indices inside the array or outside. Checks. This is automatically done in Java. So you will not be able, even if willingly you make a mistake, it will warn you that this is out of the bound or the boundary of the array. This index is invalid. Okay? This is reliable, but what happens? Every time you assign a reference to an array, it must be checked. This takes time. Imagine if you have millions of arrays, or automatically created, generated, thousands in your program, hundreds of thousands, that will take time. If we compare it to C, well, C has no such functionality. It would be faster for sure for the same program. So this is reliability versus cost of execution. There are many other examples, but this is an extremely obvious example. You can think about it. Writability and readability. So if we think about readability versus writability, and I explained about this before while explaining about expressivity, I said sometimes we can write a sentence, express it in a full way, but what happens is the problem is readability. It becomes extremely complex for reading it. Now think about this. I'll give you a very good example from a language called APL. And surprisingly, this language is named after a very funny, actually, a consideration of its own name. The author, or actually the inventor of this language, called it a programming language. A programming language. So A from A, programming, to P, and language L, APL. It's a programming language. This is its name, okay? So it's a bit weird, but that's it. So in this language, what we have a lot of ways to actually have certain assignment statement. We have very powerful operators, a lot of symbols that allow us to have complex computations or assignments. So we may have like one line that makes maybe 10 or 20 lines in other languages for computation. But how about the readability? If you are not very familiar with this language, then in that case you'll not be able to read this and understand what's going on. And the more advanced these symbols become, the harder for you to recognize the exact procedure or the meaning of the statement. Writability again versus reliability. Well, if the program is extremely writable, we may end up with a problem with reliability. I give you a very good example from C++ and Java. C++ has pointers and they are extremely powerful and flexible. But the problem with pointers is that they are unreliable. Why? Why they are unreliable? Pointers actually they are data type, or actually one type of the data types that hold the address of another data and they point to it. So if we point to data by two pointers, now we have two references to the same data. We may access the data by one of those. The data will change. The other pointer also pointing to this data will point to a data which is changed. And usually this creates confusion. This is just one type of the problems that we have with pointers, okay? In Java, this functionality or this kind of procedure is not available. We can reference things, but we cannot have pointers. Referencing in Java allows you to hold the address of whatever you are trying to create. Let's say an array, you can hold this address, reference, its own reference. But it's not by a procedure of pointer. An object, you can hold its own reference to a project. So ultimately it's an address, okay? So this is the idea, okay? And that's what we call trade-off between different factors in programming language. This is the end of this session. We will have the final and last session for this chapter. Until then, have a good time. Goodbye.